Right now, while you are reading these words, a machine the size of a small car is moving through a region of space where nothing built by human hands has ever traveled before, sending back a signal that has left NASA's own engineers using a word they almost never use in public: impossible. Not unexpected, not surprising, impossible. This is Voyager 1, a spacecraft older than the personal computer, older than the internet, older than almost every person currently working to keep it alive. It runs on a fraction of the electricity your kitchen kettle uses in a single second. It was built to last 5 years. It has now been operating for nearly 49. And in the last few months, NASA has confirmed something about this spacecraft that does not fit inside the models scientists have relied on for decades. Something so strange that the very system built to tell engineers where Voyager 1 is pointed in space has started reporting readings that do not match where the spacecraft is actually pointed at all. A machine 15 billion miles from Earth appears, in some sense, to not know where it is anymore. And that is only the beginning of what has NASA's attention right now, in the summer of 2026. Because this spacecraft is also weeks away from crossing a threshold no human-made object has ever crossed before, running on a power supply that is disappearing 4 watts at a time, and carrying inside its oldest data a mystery about the space between the stars that nobody has been able to solve. Stay with me, because by the end of this, the phrase edge of the solar system is never going to sound the same to you again. Start with what NASA actually confirmed, because it is worth being precise about it. In the spring of 2026, engineers at the Jet Propulsion Laboratory began noticing something wrong with Voyager 1's attitude articulation and control system, the onboard system responsible for keeping the spacecraft's antenna pointed at Earth with the kind of precision that, at this distance, allows a signal to be found and read at all. The readouts coming from that system were not matching the spacecraft's actual motion and orientation. In plain terms, the instrument responsible for telling the spacecraft, and by extension its human operators, which way it is facing, was reporting numbers that did not line up with reality. Suzanne Dodd, the project manager for both Voyager missions at JPL, described it publicly in terms that were careful but unmistakable. A mystery like this is part of what happens at this stage of the mission, with 2 spacecraft now pushing nearly 50 years old, decades beyond anything their original designers ever planned for. Voyager 2, its twin, was checked and found to be operating normally. The anomaly was isolated to Voyager 1 alone, and because the AACS is the system responsible for keeping the high-gain antenna aimed precisely enough at a planet 15 billion miles away to maintain any communication at all, an anomaly here is not a side issue. It sits at the center of whether this spacecraft can keep talking to us at all. To understand why this matters so much, you have to understand what Voyager 1 has already survived, because this is not the first time this exact spacecraft appeared to be slipping away from us. Go back to 2023. For 5 months that year, Voyager 1 kept transmitting a signal, faithfully on schedule, the way it had for nearly 5 decades. But the signal itself had become unreadable. Not silence, not static. Gibberish. Scrambled, corrupted data that the team at JPL, after decades of experience parsing everything this spacecraft had ever sent, simply could not decode. The cause, once they finally traced it, turned out to be both small and devastating. A single memory chip inside the spacecraft's flight data system had physically degraded after 46 years of continuous exposure to cosmic radiation. A piece of 1970s hardware, smaller than a fingernail, quietly corrupting the exact section of code responsible for formatting and transmitting scientific data back to Earth. No alarm had gone off. There was no warning. It had simply failed, the way something built in an era before modern radiation hardening techniques eventually will. The challenge was not diagnosing the failure. The challenge was fixing it from 15 billion miles away using nothing but radio waves. That took roughly 22 hours to reach the spacecraft, and another 22 hours for any response to make its way back to Earth. Every single test, every diagnostic, every attempted fix required a minimum of 44 hours just to complete 1 round of communication. Engineers would study the incoming data, form a theory, write a set of instructions to test it, transmit those instructions, and then simply wait for nearly 2 full days before finding out whether the theory was right, wrong, or had made things worse. There was no way to intervene mid-attempt. There was no way to undo a bad command the moment it went wrong. Every single instruction sent across that gulf carried the quiet possibility that a single mistake, executed once on a machine with no manual override and no repair mission remotely possible, could end the entire mission permanently. The team worked through it for months, methodically, under a kind of pressure that most engineering problems never produce, and eventually found a solution. The corrupted code could not be repaired in place, but it could be relocated, broken into smaller pieces, rewritten to function correctly from new locations in the spacecraft's limited remaining memory, and carefully stitched back together. It was, in effect, remote brain surgery performed across a 44-hour communication delay on a machine built during the Ford administration. By mid-2024, Voyager 1 was transmitting clean, complete, readable data again. It had come back from something that could very easily have ended the mission for good, and it came back with more to tell us. Which brings us to what it has actually been telling us, because the AACS anomaly and the 2023 chip failure are only the mechanical half of this story. The other half is what Voyager 1's instruments have been recording since it crossed into interstellar space in 2012, and this is where the word impossible starts to earn its place. For decades before Voyager 1 reached that boundary, physicists had built detailed models of what interstellar space should look like based on everything at home. Those models largely agreed on one point. The plasma that fills the space between stars should be relatively calm, thin, cold, and quiet, drifting slowly with little dramatic structure, a kind of cosmic waiting room between star systems. Starting in 2017, the plasma wave instrument on board Voyager 1 began picking up something that flatly did not match that picture. A persistent narrow-band emission, a faint but continuous hum in the interstellar plasma that, according to the models built to describe this environment, should not exist in the way it does. Not a one-time spike that could be waved away as noise. A signal that has now persisted, on and off, for years, detected across a stretch of interstellar space exceeding 900 million miles. Roughly 10 times the distance between Earth and the Sun. Researchers who published their analysis in the peer-reviewed journal Nature Astronomy were direct about what this means. Interstellar space is not the quiet, uniform void the models described. It has structure at every scale, from distances you could measure in meters up to distances measured in millions of miles. It is, in a very literal physical sense, turbulent, and that turbulence was completely invisible to us until the first instrument we ever placed inside interstellar space started reporting it back. Before going further into what that emission actually means, it's worth remembering how Voyager 1 got here in the first place, because the mission was never supposed to reach any of this. It launched on September 5th, 1977, 16 days after its twin, riding a faster, more direct trajectory built to sling past Jupiter and Saturn before curving up and out of the plane of the solar system. NASA's own planning documents from the era expected the mission to wind down sometime around 1981 or 1982. A modest, successful flyby program, a handful of photographs, and then silence. Instead, it reached Jupiter in March 1979 and sent back the first close, detailed images of that planet human eyes had ever seen. It reached Saturn in November 1980, using the planet's gravity for one final slingshot that also gave it a close pass by the giant moon Titan, a maneuver that traded away any chance of visiting Uranus or Neptune in exchange for speed and a straighter shot out of the solar system. And then, in February 1990, long after its primary mission had technically ended, it turned its camera backward at the request of Carl Sagan and captured Earth as a single pale blue pixel suspended in a beam of scattered sunlight. An image that became one of the most quietly influential photographs ever taken, precisely because it showed how small everything we have ever known actually is from that distance. It kept going after that. It crossed the heliopause in 2012, becoming the first human-made object to physically leave the solar system, and it kept transmitting the entire way through, which is the only reason any of what follows was ever possible to detect at all. Sit with that for a second, because it is easy to let the phrase unexplained plasma emission slide past without registering what it actually implies. Every model of the space beyond our solar system that existed before 2017 was built from the outside looking in, assembled from telescopes, theory, and mathematics, never from direct measurement taken inside the environment itself. And the first instrument ever placed inside that environment is now telling us those models missed something fundamental. Scientists have not yet settled on exactly what is causing the emission. There are two competing explanations still being debated. One possibility is that it comes from thermally excited plasma oscillations, the natural vibration of charged particles interacting with their surroundings, a genuinely significant finding, but one that would still fit inside existing physical frameworks without requiring them to be torn up and rebuilt. The other possibility is that Voyager 1 is detecting something called quasi-thermal noise, a different physical mechanism entirely, one that encodes information about plasma density and temperature in a way that would force a substantial revision of how the interstellar medium is modeled. Telling the two apart requires either more data from Voyager 1 itself, which is producing less of it every year as instruments are shut down to conserve power, or an entirely new mission built specifically to study interstellar space directly. No such mission currently exists. None is currently funded. If one were approved and launched today, it would not reach the heliopause for at least another 25 years. which means the question Voyager 1 raised in 2017 may simply stay open for a generation, regardless of how badly scientists want the answer. Then there is the magnetic finding, which Ed Stone, the mission's longtime project scientist, called one of the most remarkable results to come out of the entire crossing. For decades, one of the foundational assumptions about the heliopause was that the sun's magnetic field on one side and the galaxy's magnetic field on the other would remain cleanly separate, two distinct systems, meeting at a boundary but not really interacting. What Voyager 1 actually found, once it crossed into interstellar space, was that the two fields are connected. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, appeared to be interacting with the galactic magnetic field outside through a process called magnetic reconnection, where field lines from different sources rearrange themselves and release energy in the process. The solar system is not magnetically sealed off from the galaxy around it. It is linked to it, exchanging energy across the boundary in ways no model built before that crossing had accounted for. That is not a footnote to the mission. If the relationship between our solar system and the interstellar environment surrounding it is more dynamic and more energetically connected than the models assumed, then the entire framework scientists use to understand how the heliosphere shields Earth over geological timescales needs a second look. The heliopause is not simply a line on a diagram, it is a shield, deflecting the most energetic and dangerous cosmic radiation from reaching the inner solar system at full strength. And Voyager 1 is telling us that the environment pressing against that shield from the outside behaves in ways nobody had fully modeled before it got there to check. Now put the mechanical mystery and the scientific mystery side by side, because this is where the story becomes genuinely urgent rather than simply strange. Voyager 1's ability to keep sending any of this data back depends entirely on its dwindling power supply, and that supply is running out on a strict, unforgiving schedule. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, devices that convert the heat given off by decaying plutonium-238 into electricity. At launch, Voyager 1's 3 generators produced roughly 470 watts. Today, nearly 49. Years later, that output has fallen to somewhere around 245 to 250 watts, and it keeps dropping by about 4 watts every single year. A slow, mathematically certain decline with no way to pause it, reverse it, or refuel it from 15 billion miles away. Of the 10 scientific instruments Voyager 1 launched with, 7 have already been permanently switched off, not because they failed, but because there was no longer enough power to keep them running alongside everything else. In April 2026, engineers made the difficult decision to shut down the low-energy charged particle instrument, one of the instruments that had been collecting data almost continuously since 1977, purely to buy more time for the systems that remain. Every one of these decisions is effectively permanent. There is no way to switch an instrument back on once it has been sacrificed to save power, at least not under normal circumstances. Except NASA is not simply accepting that decline without a fight. Right now, engineers are working on an experimental procedure they have nicknamed the Big Bang, an attempt to restructure how power flows through Voyager 1's remaining systems all at once, in a single coordinated reconfiguration, rather than through a series of smaller, incremental changes. The logic behind doing it all simultaneously rather than gradually comes down to risk. A slower, step-by-step approach would spend more time sitting in unstable, half-finished configurations, and those in-between states are exactly what tends to trigger the spacecraft's automated fault protection system, the safety mechanism that begins shutting things down. On its own, the moment it senses power demand exceeding what the aging generators can supply. Because the procedure is untested, and the stakes of getting it wrong are permanent, the team is trialing it first on Voyager 2, which currently has a slightly larger power margin and sits somewhat close, to Earth, making it the safer place to risk something this drastic before attempting it on its more power-starved twin. If the tests on Voyager 2 go well, the same maneuver is expected to be attempted on Voyager 1 no earlier than July of this year. And if it works, there's a real possibility that the low-energy charged particle instrument, the one just shut down in April, could be switched back on. Nobody on the team is promising that outcome. But with a mission that has spent 49 years defying every expectation set for it, nobody is ruling it out either. And in the middle of all this, a date is coming that has nothing to do with instruments, chips, or power budgets, a date fixed by nothing more than distance and the speed of light. On November 18th, 2026, at 2:16 a.m. Pacific Standard Time, Voyager 1 will cross 1 light day from Earth, a distance of roughly 16 billion miles. At that point, a radio signal traveling at the fastest speed anything in the universe can travel will take a full 24 hours just to reach the spacecraft, and another 24 hours for any reply to make its way back. Send a command on a Monday morning, and you will not know whether it arrived until Tuesday morning, and you will not hear back until Wednesday. No human-made object has ever been that far from Earth while still transmitting, still functioning, still telling us something about the universe it is moving through. And Voyager 1 will not stop there. Every hour it travels roughly another 38,000 miles deeper into interstellar space. The communication delay will keep growing. The power will keep shrinking. And sometime in the early 2030s, most likely, the last usable signal will make its final 24-hour crossing back to Earth, be recorded, and that will be that. Even then, Voyager 1 does not stop moving. There's nothing out there to stop it. No atmosphere to create drag, no nearby gravity strong enough to meaningfully pull it off course. It will simply keep traveling in a straight line at roughly 38,000 miles an hour through darkness that has no meaningful end on any human timescale, carrying with it the Voyager Golden Record, a gold-plated copper disc holding greetings recorded in 55 human languages, the sound of rain falling in a forest, the sound of ocean waves, the sound of human laughter, 90 minutes of music drawn from across the history of human civilization, diagrams explaining our basic physics and mathematics, and a map built from the positions of pulsars, showing exactly where in the galaxy this all came from. Carl Sagan, who helped design it, called it a message in a bottle cast into the cosmic ocean, and that description has only become more literal with every year the spacecraft keeps moving. That record will still be traveling long after the sun swells into a red giant and swallows the orbit of the Earth. It will still be traveling after every human city, every archive, every word we've ever carved into stone has been worn away by geology and time. It may be the single most durable object our species has ever built, and it is riding on a spacecraft currently kept alive by less power than the light bulb over your bathroom mirror. Here's what actually sits at the center of this story. Underneath the AACS anomaly and the memory chip failure and the Big Bang gamble and the light day milestone still weeks away. Right now, in 2026, the only live scientific instrument our species has ever placed inside. Interstellar space is nearly 49 years old, built with technology that predates the personal computer, running on a fraction of the power in your refrigerator light, and sending back data that has already forced a rewrite of how scientists think about the structure of interstellar plasma and the magnetic relationship between our solar system and the galaxy around it. And that has NASA's own engineers using the word impossible to describe what its own attitude control system is currently reporting about its own orientation in space. We have built spacecraft that are bigger. We have built spacecraft that are more powerful, that cost more, that carry more advanced technology by orders of magnitude. None of them have told us what Voyager 1 has told us, because none of them had the one thing Voyager 1 had, the sheer stubborn endurance to keep. Going long enough to actually get there and stay long enough to keep reporting back. There are questions about the universe that can only be answered from inside it, not from a telescope on the ground, not from a satellite in Earth orbit, not from any mission that has yet been built to follow in Voyager 1's path. Right now, we have exactly one machine out there doing that job. And it is old, it is confused about its own orientation, it is running on a power supply with a hard, ticking expiration date, and it is still talking to us. As long as it keeps transmitting, the only responsible thing to do is keep listening, because when it finally goes quiet, some of the most important questions it raised about the space between the stars are going to stay unanswered for a very long time. If stories like this are what you come here for, subscribe and turn on notifications, because we're going even deeper into what's actually happening at the edge of the solar system next time, and you'll want to already understand what's at stake when Voyager 1 crosses that one light day threshold this November.